sampling distributions. And today we're going to focus on the sampling distribution of sample means. Today the parameter we're looking at is mu, which is the population mean. And the statistic we're going to use to estimate that is x bar, the sample mean. And then we'll also be using the standard deviation. Okay. So remember, mu is the parameter, and x bar is the statistic. Recall that for a sampling distribution, any statistic, being a random variable, has a probability distribution, and that includes x bar. And the probability distribution of the statistic is sometimes referred to as its sampling distribution. Okay, so we're going to take multiple random samples, and we're going to calculate many different sample means, and then we're going to graph them into a probability distribution. Okay. So here's an example. We randomly sampled 30 adults and asked them what their IQ is. We calculated the mean IQ of the 30 subjects, and then we graphed the sample mean below. So doing that one time would represent one of these dots. Okay. We repeated this process 1,000 times, which means there are 1,000 dots on this picture. Okay. So this is a meta-experiment, and the result is a sampling distribution of the sample mean below. Okay, so n equals 30 means that each sample was 30 people. And we got all 30 people's IQs, and then we averaged them out and put a dot on this graph. Okay, and we did that 1,000 times. This is the mean of those 1,000 sample means. Okay, so we typed in all 1,000 sample means from this graph and figured out that the average of those was 100.35. And then the standard deviation of those 1,000 dots is 2.833. Okay. Now, sampling distributions of sample means have properties, okay, just like they did for proportions. The first rule should look very similar to how it looked for proportions, but the mean of all the x bars will equal the population mean. So when I say the mean of the x bars, I'm talking about all of these dots. That the mean of all of those points will equal the population mean. Okay? And we have a way to describe the sampling variability, like how much do these samples vary by, and that's this equation, the standard deviation of x bar. So this is the standard deviation of those 1,000 dots. And that will be equal to the population standard deviation divided by the square root of the sample size. Okay? The bigger the sample size, the smaller this standard deviation is going to be. Okay, so that's a way of saying the bigger the sample size, the more accurate our samples will be. Okay. Another property of sampling distributions of means is that if you take a large enough sample, our sampling distribution will be approximately normal. I think if you look carefully here, if I drew a little line, the rough shape of this is a bell-shaped curve. Okay, and remember, when you have an approximately normal distribution, that means I can now use a z-score. Okay, and we're going to be using the sample mean as our x. All right, and this number right here is a very good estimate of the population mean. Okay, now those three are only true if the following conditions are met. And you'll recognize these from our sample proportion lesson. The first two are exactly the same. We would like a sample taken that is random, okay, and the sample taken is less than 10% of the population size. Remember, we don't want to lose independence between selections. And then the third condition, this is the one that varies from the proportion lesson, the sample size is at least 30, okay, which another way to say that is n is bigger than or equal to 30. So if the sample size is that large, we can assume the sampling distribution will be normal. Or if you know that the population distribution is already normal, then any sampling distribution you create from that will also be normal. So there are certain variables that we know already that are normally distributed, like the length of pregnancies, the height of males, the height of females. There's thousands of variables that are already normally distributed. So if we know the data we're collecting is coming from a normal distribution, we can assume then the sampling distribution is also normal. But if we don't know that the population is normal, then we'd have to check that our sample size is at least 30. So, just a quick refresher, why do we want a random sample? Because we want our samples to cluster around the actual mean, okay? If we don't take a random sample, they might be biased and we might miss the mean, so these are off. Remember, when we take that average of those samples, they're gonna land somewhere in the middle of the group. And we'd like that to land in the bullseye, and for that, we need a random sample. The second condition is that the sample size that was taken is less than 10% of the total population size. Remember, when we sample, we want to be careful that there's independence between selections. And if we draw more than 10% of a population without replacement, we are in danger of losing this independence. Okay, so we just have to be sure we're not selecting so many people from the population that we're changing the probability of any certain selection. Think to our M&M example from before. Number 3, n has to be greater than or equal to 30 or a known normal population. So this is the minimum sample size needed in order for our sampling distribution to be approximately normal. Now, if we know the population is normal to begin with, then the sampling distribution will be approximately normal regardless of the sample size. So there's kind of two situations to deal with here, okay? If it says the population is normal in the question, then we can assume the sampling distribution is. If there's no information about that in the question, then we're looking for the sample size to be 30 or more. So, what we sampled here when I estimated the sample is that on planet Earth, the mean IQ is 100 and the standard deviation is about 15. And it's been this way. They figured for hundreds of years, okay, that the mean IQ on the planet has always been about 100 and the standard deviation is about 15, okay? So I was sampling from that population when I made this distribution, and I just simulated that distribution, okay? So remember, this is 1,000 samples taken, okay? And the mean of all these samples should equal the population mean. And the mean of all of these samples was 100.354. So very close, okay? And that's an excellent estimate of the population mean, okay? Now, the sampling variability of this graph should be equal to, since our conditions were met, should be equal to the standard deviation of the population, which we know to be 100, divided by the square root of the sample size, and my sample size was 30. So if I make this calculation, just type it into my calculator, I get 2.74. Okay, that should be the variability of this sampling distribution. The program I used to make the simulation actually calculated the standard deviation of the sampling distribution, and you can see they are very close. Okay, within 1/10 of each other, actually 9/100ths, within 9/100ths of the actual answer. So this would be the theoretical number, and what it should be in multiple samples and millions of samples, and this is what I actually got when we did this meta experiment 1,000 times. So you can see the theoretical came very close to predicting my experimental results. Okay, and then it says if we take large enough samples, the sampling distribution will be approximately normal. Well, I have purposely sampled 30 so that this would be approximately normal. Now, IQs happen to be approximately normal in the population. So either way, this would have been approximately normal. Okay? So by following those conditions, the random sample and the 10% rule and the sample size rule, that allows us to use these equations to predict information about the sampling distribution without actually doing the samples, okay, without actually doing the simulation of 1,000 samples. If the conditions are met, I can jump right to these formulas, okay? And then also I know that it's approximately normal, so that I can draw bell-shaped curves and use z-scores to answer questions, okay? So let's do a couple examples. It says a bottling company uses a filling machine to fill plastic bottles with cola, so maybe it's Coke or Pepsi. The bottles are supposed to contain 300 milliliters. if in fact the contents vary according to a normal distribution with mean 298 and a standard deviation of 3, what is the probability that an individual bottle contains less than 295 milliliters? So, since it tells me that this was a normal distribution for the population, I can draw a bell-shaped curve, and I can fill in the mean they told me. They said it was a normal distribution with mean 298 milliliters and a standard deviation of 3. My question is, what's probably that an individual bottle contains less than 295? So 295 would be over here. And I'd try to find that probability. Now, since we know the population is normally distributed, I just use a z-score. So my z would be 295 minus 298 over 3. So my z-score is -1. And then I would do normal CDF, -10 to -1, and that's about 16%. So there's about a 16% chance that I would get a bottle chosen randomly that would have less than 295 milliliters in it. Okay, so that's an old z-score problem from Unit 1 at the very beginning of the course, where if I know I have a normal distribution, I can just use a z-score to find a probability. B is going to talk about a sampling distribution, though. B says, what is the probability that the mean contents of the bottles in a 6-pack are less than 295 milliliters? So now I'm not talking about one bottle anymore. I'm talking about a 6-pack. Okay? So now I'm talking about a sampling distribution, because in that 6-pack, I'm going to find the average amount in the bottle. Okay? So in order to do my next, to answer this question, I need to check conditions first. And the first condition is a random sample. Now it doesn't tell me that, but I think we can assume a 6-pack is a random sample. Okay, like any 6-pack wouldn't be any different than any other. Number 2, can we assume this 6-pack is less than 10% of all bottles produced? I think we can assume that, right? Even if it'd be less than 10% of all bottles probably on the shelf at your Cub, and just think about all the places that sell soda. And then 3, our sample size is not 30, but we know the population distribution was normal. So I can say population distribution is normal. So because of that, then I know my 3 conditions, or my 3 properties are met, that the mean of all my samples should be the population mean, and the standard deviation of my samples should equal the population standard deviation divided by the square root of n. Now, because all my conditions are met, I know that I can draw a normal distribution, and that distribution will have the mean of the population, which is 298, and it will have a standard deviation that I can find using this equation. So it'd be the population standard deviation of 3 milliliters divided by the square root of the sample size, which is 6, which is 1.22. Okay, so this blue graph that I have drawn on the bottom, this graph represents the meta experiment of drawing infinitely many 6-packs randomly from a population of bottles, and this is what that sampling distribution would look like. Okay, so this is a graph of all of the mean amount of cola in these 6-packs, and think about drawing, thousands of samples. Okay, the mean of this graph would be 298, and the standard deviation of this graph of the means of 6-packs would be 1.22 milliliters. So now my question is, what's the probability that the mean contents of the 6-pack are less than 295? That's the same question as before. So 295 goes here. So the only difference is when I do this problem, I'm looking at 6-packs, I need a different standard deviation. So my z-score would be 295 minus 298 over 1.22. And I get a z-score of negative 2.46. And then again, I would look that up. So I'd go normal CDF, negative 10 to negative 2.46. And when I round my answer, I get about a 1% chance. Okay? So, the chance of finding one bottle, okay, that contains less than 295 milliliters was 16% from question A. But the chance of finding a whole 6-pack averaging less than 295 milliliters is only 1%. Okay? So only one 6-pack out of 100 would average less than 295 milliliters. Okay? So one thing to notice here, it's harder for a sample mean to be further away from the population mean than it is for an individual measurement. Okay? One bottle was only, there's only a 16% chance of one bottle being there, but there's only a 1% chance of finding a 6-pack that averages that. So averages are always less variable than individual amounts. Okay. Let's do one more. A company that owns and services a fleet of cars for its sales force has found that the service lifetime of disc brakes varies from car to car according to a normal distribution, with a mean of 55,000 miles and a standard deviation of 4,500 miles. So what is the probability that a car's brake pads last for more than 60,000 miles? So since they told me this is a normal distribution, I know that the mean is about 55,000 miles, and the standard deviation is 4,500 miles. And the question was lasting longer than 6,000. 6,000 or 60,000 is here. That's my shaded area. So this is just a z-score question because we're talking about one individual car, not a sample of cars. And my z-score ends up to be 1.11. And my the probability of that happening, which I'll do normal CDF, 1.11 to 10 is equal to 13%. So there's a 13% chance of your brake pads lasting more than 60,000 miles. Okay. Now, B says the company installs a new brand of brake pads on 8 cars. What is the probability the average lifespan of the brake pads on these 8 cars is more than 60,000? So I'm talking about the average of these 8 cars. That's going to be an X bar. So I need to know, what does that sampling distribution look like? Okay. So first I'd have to check conditions. And remember, the first condition is a random sample. And they don't say anything about it in this problem, so we probably have to say something like assume an SRS of 8 cars was selected. Okay. Number 2, we can assume 8 cars is less than 10% of all cars made. And I think we can safely assume that, right? And then the third thing would either be a sample size of 30 or more, which we don't have, but they did tell us that the population was normal to begin with. So we can say population normal. Okay? So that means that the mean of my sampling distribution will equal the population mean, and that the standard deviation of my sampling distribution will equal the population standard deviation over the square root of n. So I can draw my bell-shaped curve, and the mean was 55,000 miles. The standard deviation was 4,500. Now, I need to divide that by the square root of the sample size I took, okay? Because the sampling distribution will not be as variable as the individual population. So the sampling variability of this sampling distribution would be 1,590, and we'll do 91 miles, rounds to 91. Okay, so taking a sample of 8 cars reduces my sampling variability, okay? the average of 8 cars will only vary by 1,591 miles. Okay. So now I want to check the same question I had before. What's the chance of these cars averaging more than 60,000 miles on their brake pads? So it's going to be another z-score, but with my adjusted standard deviation. So it's 60,000 minus 55,000 over 1591. So my z-score ends up to be 3.14 pi. And then when I look this up using normal CDF, I end up getting 0.0008% chance. Okay, so that is extremely small. Obviously, my picture doesn't even look quite to scale. Okay, so if you think about that, that's the 10th place, the 100th place, the 1000th place, the 10,000th place. So out of 10,000 samples of 8 cars, we would only expect this to happen 8 times. Okay, so given this information, there's virtually no chance of getting 8 cars that average 60,000 miles or more on their brake pads. Okay, pretty decent chance of finding 1 car to do it, a 13% chance, but finding 8 cars that would average that if they were selected randomly, nearly impossible. Okay. All right, so don't forget to check conditions when you do these problems, and remember that these conditions allow you to describe the sampling distribution without doing a meta experiment. Okay, as long as the conditions are met, we know what the parameters are of this sampling distribution as long as we know the sample size. It's something to keep in mind that as we sample larger and larger samples, our standard deviation will get smaller and smaller. Okay, and I think that makes intuitive sense. If you think about larger samples, will be more accurate. Okay, good luck with the sampling distribution of sample means.